In this second part of the lecture, we will study how to calculate the sample size in cases in which the correlation is measured in some more specific way rather than the Pearson correlation coefficient. And all of our examples will, or our cases will be related to only one sample, so we will not be comparing the agreement between multiple samples. And let's start with the first one. So the first one is, let's say that you want to determine if you can predict the mass of myeloma cells, that is a kind of cell, from the extent of bone lesions, hemoglobin level, and serum calcium level. So you have three variables, and these three variables will try to predict the mass of this kind of cells. So you will collect for a number of tissues, you will collect these three variables, and from these three variables you will construct a regression on the mass myeloma cells. This regression doesn't need even to be linear regression, so it can be even non-linear regression. And you will compute the multiple correlation coefficient that we will see now what it is. And you want to have a statistical power of 90% if the multiple correlation coefficient is larger than 0.7. Okay, so let's see. So you will construct a model, a regression model in this way, whatever function this is. So you will try to predict the cell mass as a function of the bone lesion, hemoglobin, and the serum calcium. And once you have your predictions, you can make the following calculation. The calculation is this. So you will have your observations, and you will have the difference between your observations and your predictions. So if you make perfect predictions, then this will be 0. And you divide that by your observations minus the mean of the observations. This is the simplest model you can have. This is just substituting by the mean. So what you're measuring here is whether your predictions are much better than a very simple model. So if you make very good predictions, then if you make perfect predictions, then this will be 0, and rho squared will be 1. If you make very bad predictions, then you will do almost as bad as a simple constant. So this ratio will be close to 1, and then this close to 1 value. The ratio is close to 1, so rho squared is close to 0. So the test that you are checking is whether this is actually r squared, and here you recognize the sum of squares of the model divided by the sum of squares of the total sum of squares, and then this is the sum of squares of the residuals. Okay, so the test that you are trying to do is there is a mistake here. This should be a smaller or equal. So is whether r squared is larger than 0 or it is a smaller or equal 0. Okay, so again, you need a statistic that you know how it is distributed. So in this case, the statistic is f. F is defined as this. So the sum of squares of the model divided by the number of degrees of freedom of the model. The number of degrees of freedom of the model is the number of predictor variables in the model. So if you have 3 predictors, you will have k equals 3. And then divided by the sum of squares of the residuals divided by the sum of squares of the degrees of freedom of the residuals, that is the number of samples minus k minus 1. And under the null hypothesis, this f is distributed like this. Under the alternative hypothesis, f is distributed like this, where this first term is the non-centrality parameter, and this k n minus k minus 1 are the 2 degrees of freedom. So you need to find a critical value such that from that critical value to the right you have alpha, from that critical value to the left you have beta. So yeah, it is again not an easy equation to solve, but computers know how to do that, and what you get is n equal 20. And you don't need so many, because in our test you see that 0.7, that is when we want to have 90% of a statistical power, is relatively far from 0. That is the reference value. So as it is far, it will be easy, and then we will require very few samples. The intra-class correlation is a different way of measuring the correlation between samples in this case. Okay, so I think this is a good way to conceptualize what is the intra-class correlation. So let's say that you have two completely unrelated individuals that are randomly selected from a general population. Then you have n equal 2, you have two independent samples. So you have, because the samples are independent, you will have an intra-class correlation that is 0. And then you, instead of two completely unrelated individuals, you take two siblings from the same household. So now the response of these two siblings will be more correlated to each other. So you don't have two completely independent samples, but a little bit less independent. So the intra-class correlation grows a bit. Now instead of two siblings, you take two non-identical twins, and again the correlation between those two, because they have the same age, it will be a little bit larger. And then you take identical twins, two identical twins, so they are even less independent, and the inter-class correlation even grows. And let's say that you take two Siamese twins, and then these two Siamese twins, they share so much background, genetic background, education background, so that they can even be thought to be kind of a single individual. It is not like that, because their experiences are different, but you see the concept. So the two, so if two measurements are completely independent, then you have a low intra-class correlation. The more dependent that these observations are, the intra-class correlation grows. So let's say that you are interested in determining the degree of coherence between different patients evaluating different pain relievers. So for doing so, you ask, are patients, so these raters are patients, to evaluate n samples of the same pain reliever. So this is the same pain reliever, and you ask this person to rate the same pain reliever, but he doesn't know, to evaluate it once and twice, 3 times, 4 times, etc. So in this example here we have n equals 6. So you want, so if he's totally coherent, all these rates would be exactly the same one. If he's rather incoherent, then all these rates would be different. And you expect that the intra-class correlation between, so you will estimate what is the intra-class correlation from this set of measurements, this set of measurements, this set of measurements, and so on. So you expect the intra-class correlation to be between 0.7 and 0.9, so a relatively high intra-class correlation, and you want to construct a confidence interval with a confidence level of 95%. Okay, so the intra-class correlation is defined in the following way. So it is defined, so each one of the measurements is an overall mean plus something that depends on the specific rater, plus something that depends on on some noise. So if raters are very consistent, then there are large differences between raters and small differences within the raters. So this variance here, this noise, is the variance within the rater. So you would expect that the differences that you observe in these numbers, so within the rater, so if he's totally coherent, sigma epsilon will be 0. So, and then the ICC would be 1. So you expect that ICC is close to 1 if the inter-rater variances or differences are much larger than the intra-rater differences, and ICC is close to 0 in the opposite case if this is much larger than this one. Okay, so again we look for a transformation that help us to use Gaussian tools. So this is the transformation that we need, and R is the number of raters, and the variance of this set is approximately this if we have two cases, when R is equal to when R is larger than 2. And then from this Gaussian approximation we can already compute what is the sample size. So sample size is something that is related to the confidence level and then divided by the normalized effect size. And because we have two variances, we will have two formulas, one depending on how many raters you have. So in this case we have R equal 4. So R equal 4. So let's say that we know that we expect our intra-class correlation to be between 0.7 and 0.9. So we compute set, the upper bound of set, the lower bound of set. We compute the difference between the two, and we simply substitute, and we see that we will need about 28 individuals. So this low number means detecting the intra-class correlation of something that is relatively coherent. It is not too difficult. Okay, so let's study a different case. So you may remember from the first lecture on the calculation of the sample size for means this problem. So let's say that 1 month old babies awake every night, awake by night every 3 hours with a standard deviation of 0.5 hours. And we assume that the sleeping period is normally distributed. And our hypothesis is that babies that are not attended, like in an orphanage, they adapt at this age of 1 month old, and then they start to sleep longer because they are not attended anyway. So and we want to detect shifts of at least 1 hour. We do not know the standard deviation of the sleeping time because it may also change with respect to the general population, but it cannot be too far from this 0.5 hours from the general population. And we will repeat this experiment in 3 different orphanages, so that it might be that different orphanages, they have people that attend more or less these babies, and then that makes a difference. So we want to measure what is the intra-class correlation between the different orphanages. So the orphanages now become the raters, and we want to measure this ICC. So the derivation is a bit complicated, but let's see. So presume that we will take nk samples from each one of the k clusters. So we have 3 clusters that are the 3 different orphanages, and then we take nk samples from each one of them. So let's say that the variance, the mean, so the variance of our estimate of the mean will be the variance of the sleeping times between babies divided by n, the total sample size, and the total sample size can be expressed as k and k. But because babies from the same cluster, they tend to be correlated, then the actual variance is not this one. There is a multiplicative factor, that is this one, that makes that all those variances, we don't have totally independent individualities like the case of the twins, siblings, independent people from the general population. So this variance is actually, so from every measurement that we take from one of these groups, from one of these K clusters, we don't get a totally one independent measurement. So we get a little bit less. How to encode that? So we can multiply this variance by a factor that is larger than 1, and that is called the variance inflation factor. So this variance inflation factor will increase the variance of our the variance of our estimate of the mean, simply because for every measurement that we get, we don't get a totally independent measurement. So now it is simply to substitute these into the so the new n will be or the new variance will be a little bit larger, and then we can calculate the sample size, and the sample size of each one of the groups would be n, that is the sample size for completely independent samples that we would compute in this example here. So up to here we make a calculation assuming that the samples are independent. We will get an n, but then we increase this n by something that depends on the intra-class correlation. So for instance, if you want to compute the n for these, we already know how to do that because we saw on the case of the calculation of the sample size for means. So it was n equals 6, but because the intra-class correlation is 0.1, they are slightly correlated, then our sample size for each one of the clusters is a little bit larger, and you know that we have to approximate or round up always, so we will take 3 samples from each one of the K orphanages. So in total we have a sample size of 9 rather than a sample size of 6. And last we will analyze this Cohen's kappa. So Cohen's kappa is a way of measuring the correlation between two variables x and y when they take discrete values. So, and these discrete values are ordinal. So for instance, let's say that we are developing a new antidepressant that is presumed to be equivalent to another one that is already marketed, and then patients are divided in 2 groups. One of the groups will receive the new one, the new drug, while the other group will be given the reference drug. After 2 weeks of treatment, patients are asked to say whether they feel better or not, and so we have 3 possibilities: better, the same, or worse. And after a period of washout, the 2 groups will be interchanged, so each patient will take the other treatment. And how many patients do we need in each one of the groups to show that kappa, that is this a way of measuring correlation, is larger than 0.8? And we want to check, we want to test whether the kappa is larger than 0.8. Okay, so let's see. So in each one of the for each one of the patients, we will have 2 evaluations of the two drugs. So we will have for drug 1, this person is feeling better, and for drug 2, this person is feeling better too. And then this person is feeling better and this person is feeling the same. So we want to detect whether this column has an agreement of 0.8 or larger with this column. How to define this agreement? This is the kappa. Okay, so we will denote as Pij the proportion of cases in which the first drug obtained a label I and the second drug a label J. So this would be better, better. This would be better, same. So we compute what is the proportion of people in all patients getting better, better, and the proportion of people having better, same, and so on. And we will denote as PO the observed proportion of agreement. So the observed proportion of agreement is the sum of all proportions in which they had better, better, same, same, worse, worse. And then if these two evaluations are independent, then the expected proportion of agreement, just by chance, they would be these ones, Pi dot times P dot I. Okay, so what is Pi dot? Pi dot is the sum for Pij with and we sum over J. So that is why J is substituted by a dot, and P dot J is the opposite. So I is substituted by so we sum over I. And this, for instance, Pi dot would be better, 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 same, better, worse. So we have to add those three proportions, and we multiply these two expected proportions, and this would be the expected value of agreement just by chance. Okay, so the Cohen's kappa is defined in this way, and our test is of this kind. So the variance of this estimate of this kappa can be calculated like this, can also be calculated like this, and at the end, well, it is some function of kappa divided by n. Okay, so now we can use Gaussian tools to calculate this sample size. So the sample size will be the term depending on the confidence level, the term depending on the statistical power, and the normalized effect. And we have already seen many times these normalizations going up into the numerator. So yeah, would be this. And we can simplify this a bit. So if we want to compute the confidence, so if instead of making a test we want to compute the confidence interval of length delta, then this is the formula. Okay, so we substitute in our case, and so let's say that we assume that the kappa will be 0.8. So let's say that we want to have a statistical power of 90% when kappa is 0.9. So, and let us also assume that the probability of feeling better with both drugs is 0.5, feeling the same 0.3, the feeling worse is 0.2. Okay, so the expected probability of agreement is this one, and then this f kappa 0 is simply going to here substituting, and be careful with the substitution. So f kappa 0 is this one, f kappa 1 is this one, and then we simply have to substitute in this formula, and we have n is equal to 200, so about 200 people. So we see that it is not so easy to show that some labels are consistent between different people. Okay, so in general what we have seen is that for the correlation for Pearson correlation, we have kind of Gaussian-like formulas, and these are relatively simple to calculate. And when we go into more sophisticated ways of measuring correlation, then things might get much more complicated, as we saw for the case of multiple correlations. And this would be all for the correlation, and see you in the next lecture.